Good evening, everybody. We'd like to welcome Dr. Matthew Malek from the University of Sheffield, who's been one of our, shall we say, regular speakers over the last few years. Matthew may be the only physicist you ever met who has gone scuba diving in a particle physics detector. After starting uni with the intention of a career in cognitive psychology, he accidentally got sidetracked into particle physics. Matthew cut his professional teeth at the Kamioka Observatory in Japan, where he earned his doctorate by using the Super Kamiokande experiment to hunt for relic neutrinos from the ancient supernova in the early universe. After completing his degree, Matthew continued to wander the far corners of the globe, studying ultra-high energy cosmic rays at the Pierre Auger Observatory in Argentina, and then searching for dark matter in Italy's Gran Sasso Underground Laboratory. In 2006, he made Oxford his home, and in 2010, he returned to his first love, neutrino research. When not probing the mysteries of the universe, Matthew can be found ringing church bells, running, swimming, cycling, or hiking. He's an avid theatre buff and recently completed his long-term goal of seeing every one of Shakespeare's plays performed live on stage. So, can we please put our hands together and welcome Dr. Matthew Malek. Thank you.
Well, thank you very much, Steve, for that kind introduction. Let me share my screen. Can everybody hear me and see that?
We can.
Excellent. So yes, for tonight's talk, I'm going to give you a presentation on multi-messenger astronomy. So this is really the multi is the key. In order to properly cover this, actually it's a whistle-stop tour of several topics, each of which is quite interesting and could merit an hour-long talk in its own right. But in order to talk about the synergies where they overlap in what is this rapidly evolving field of multi-messenger astronomy, I need to give a summary view, a synopsis view of each of the different modes of detection so that I have time then to talk about how they work together. I hope you will enjoy, and of course, if you have questions, we can certainly have a chat at the end. So first, I'm going to ask you to think about the question, how do we look at the sky? And in fact, a little bit of a hint here is the Pierre Auger Observatory that Steve mentioned earlier is shown in this cartoon. This is actually an event display from that observatory, which we'll talk more about a bit later. So how do we look at the sky? Well, there are many answers to that question now. This wasn't always true. In fact, if we turn back the clocks just 1 century, we only had one means of looking at the sky. For most of human history, the only tool we had to look at the sky was visible light. And so what we're talking about is not only a single messenger, the photon, the particle of light, but also you see the electromagnetic spectrum here with the wavelength in meters on a logarithmic scale up above, but actually just this very narrow band of the electromagnetic spectrum where the visible light falls. Yet, despite being so limited in what we could see, we were able to take some amazing pictures of the cosmos, like this picture of the Horsehead Nebula. You all know this, of course, from your own telescopes. You can see some spectacular things. And we learned an awful lot about the universe from our own solar system to Hubble's observations that led us to see the expansion, to Fritz Zwicky almost 100 years ago now, in 1933, coming up with the realization that there's dark matter. And all of that was done with visible light as our messenger. And yet, as the 20th century went on, we learned to observe light at different wavelengths. So we've moved now from observing just this sliver of visible light to viewing light in the infrared. And you can see, for instance, this picture of Hale-Bopp taken with infrared by the Palomar telescope. And in fact, you probably haven't heard of it, but there's this new telescope called James Webb. It hasn't gotten a lot of press, so maybe it's gone under your radar. But unlike its predecessor, the Hubble Space Telescope, which used visible light, James Webb is using infrared light. And we really can learn an awful lot with infrared, in part because the expansion of the universe has shifted higher wavelengths, such as visible light. Sorry, can you hear me okay?
Yeah,
I thought I heard.
We're having technical problems on our side.
Okay.
Don't worry about it.
Okay, very good. Then I'll press on. Also, in addition to looking at light from the infrared, you can move up to more energetic than visible light, and for instance, look at X-rays. And so the Chandra X-ray Observatory was able to take this wonderful picture of a supernova remnant in Centaurus A. We're still using the same messenger, the photon, but we're going to multi-wavelength approach as different technology opens up different ways of looking at the cosmos. And then if we go to lower energies, below the energies of infrared light to radio waves, well, microwaves are a type of radio wave, and you get pictures taken every decade or so. We get a better and better look at the cosmic microwave background. You're starting with telescopes like COBE in the 90s, following up with those like WMAP in the aughts, and then Planck in the teens, giving us pictures of the anisotropy in the cosmic microwave background, which is, of course, the first light we could see that survives from after the Big Bang at about when the universe was a tender young age of 400,000 years. And we've learned so much each time we develop the technology to see in a new way. However, this talk is not called multi-wavelength astronomy. It's called multi-messenger astronomy. And so that means that we need to go beyond light. Light is a wonderful tool for learning about the cosmos. We've just seen several examples of different what we've learned from different wavelengths. But going beyond light to a multi-messenger approach means seeing other particles as well. So this chart that I've shown here tells you the wavelength on a logarithmic scale. So it's the log of the wavelength in centimeters of a messenger. And on the vertical scale, you have, again, logarithmic scale, you have the flux. So how much of it, of that messenger is there? And by flux on a log scale, what I mean is if you go from 0 to 1, you've gone up by a factor of 10. Going to 2, you've gone up by a factor from 0 of 100, and so forth. And then it's in units of energy density. So at the lower energies, most of what you have is coming from photons. For instance, this big jump here, if we were able to do this in person tonight, I would pause and ask if anyone in the audience knew what this was. Since I can't really see your hands very well while I'm sharing the screen, I'll just say this big bump in flux is the cosmic microwave background. So you've got at microwave energies, you've got a whole heck of a lot more flux by a factor of 10 or 100, because you've got the leftover radiation for the Big Bang. And then you get into visible light and higher till you get up to gamma rays, and then suddenly you don't have anything anymore. These arrows mean nothing was seen here, but it must be below these points where the arrows are, or we would have seen it. But why don't we see anything after seeing for so many different wavelengths? We see light. Why don't we see anything when we get up to these higher energies? There's two reasons. One is, as you go higher in energy, it's harder and harder to make light of those energies. That's why you've got this continual drop in flux as you go up in energy. But also, once you get to a certain energy, you reach the point where your photons can actually have collisions with other photons, specifically photons left over from the Big Bang, from the cosmic microwave background. And when you get to energies where you're getting these very energetic photon-on-photon collisions, we come to what somebody once said, forget who, somebody said something like E equals mc squared. And so you have so much E at these with photons of these very high energies that these collisions are able to produce matter particles. And so you get high energy photon collides with the cosmic microwave background photon, and out comes a positron-electron pair, a matter-antimatter pair. And so now that high energy photon is no longer available. It's been taken out of the cosmos. And that's the other reason we don't see things at these energies. So we have to look for other messengers. One of those can be neutrinos, which I'll talk about a little bit later today. Another can be cosmic rays. And in fact, we see protons or cosmic rays, which we assume are proton-like, at these energies. At lower energies, it's hard to do astronomy because charged particles like protons bend in magnetic fields. Their direction curves. That's how things like particle accelerators, cyclotrons work. You use a magnetic field to bend the path of a particle. The problem is, if something is bent in its path before it reaches the Earth, you don't really know where it came from, because if you look at the direction it came in, doesn't mean it came from that way because it's curved around to reach you here. It came from here, but you think it came from that way. At the higher energies, that's not a problem, because the more energy something has, the less it curves in a magnetic field. And so when you get up to energies like 10 to the 20 or 10 to the 21 electron volts, your protons can point back to their source as far back as 40 or 50 megaparsecs. You know, for scale, remember that our galaxy here to the center of the galaxy is about 10 kiloparsecs. Here to Andromeda is about 1 megaparsec. So we're looking at 40 megaparsecs. So that's quite a nice distance. Okay, I did also talk about how we need technology to see these new particles. So massive new observatory. It's not enough to say there are protons in cosmic rays there and there are neutrinos there. We need a way to see them if we're going to do astronomy with them. And so we've been building for the past 20 years, and we continue to build massive new observatories, such as the IceCube Observatory shown on the right and the Pierre Auger Observatory on the bottom. Both of these, of course, are cartoons that allow us to see these new messengers, neutrinos in IceCube and cosmic rays in Pierre Auger. So let's talk about them in a few minutes and explain a little bit more. But before we do, it's not just other particles that we're looking at. You know, light has a particle and a wave nature. And I've talked about cosmic other particles like cosmic rays and neutrinos here, but we can also look for other waves. And you may recall about 6 years ago, there was a big splash in the news when the LIGO Gravitational Wave Observatory made the first observation of gravitational waves. And so that's another messenger from the cosmos. And we've got photons sitting here in 2022. We've got photons at all these different wavelengths: gamma rays, X-rays, microwaves, radio waves, infrared waves. And we've got neutrinos, and we've got cosmic rays, and we have gravitational waves. So this now here is the first time where we have enough different ways of looking at the cosmos that we can start doing multi-messenger astronomy. And that's why it's such a hot topic right now, because really this is the first time we can start doing this. So let's start by talking a little bit more about gravitational waves. What are they? Gravitational waves are a strain on the fabric of space-time caused by moving masses. So what is a strain? Strain is when space-time is excuse me, compressed in one direction and simultaneously expanded in another direction. So you can see in this cartoon, for instance, if you have two neutron stars or two black holes in a binary pair orbiting each other and spiraling inwards, they make gravitational waves. And as they get closer and closer and orbit more frequently, the frequency of the waves jumps up. What is actually happening over the course of one wavelength here? So let's study just one wavelength from one trough to the neighboring trough. Let's start at the midpoint, because at the midpoint, you've got no distortion whatsoever. And then you'll go to a peak, and you've got compression of space-time in one direction, stretching in the other. And then you come back to the midpoint, and it's normal again. You drop to the trough, and now it's compressed in the direction it was stretched, and vice versa. And then you go back to the midpoint again, and all's well. And so that's what we're looking at. But if you look here, you see the vertical scale goes from 1 to -1, multiplied by a factor of 10 to the -21. That's small. That's really small. How small is that? Well, let's take a look at what 10 to the -21 means, because this is very typical. It's very, very small. You can see this is the original, from the original press release and publication from LIGO back in 2016 with the September 2015 observation that they made. You can see their own units here. You know, what we had over here is an illustrative cartoon. This is the actual data from them. And the strain, again, is in units between -1 and 1 times 10 to the -21. So how small is that? I'm going to give you an illustrative example. The first observation of gravitational waves was announced in 2016. That year, the government, the entire government budget for the UK was 760 billion pounds. That's 7.6 times 10 to the 11th pounds. In fact, let's round up to make the numbers work more efficiently. Let's round that up to 1 trillion, which is 10 to the 12th pounds. You know, what's 240 billion pounds between friends, right? Assuming that the inflation-adjusted budget, I'm not getting my toes in the water of inflation, especially not these days. Let's assume that's constant for 100 years. So if the budget for 1 year is 10 to the 12th pounds, the entire UK budget for the 21st century is 10 to the 12th times 10 to the 2, or 10 to the 14th pounds. Well, let's do it in pennies. That's 10 to the 16th pence is the UK budget for the entire 21st century. So imagine if you're trying to understand how big is 10 to the -21, imagine trying to track the government's budget for the entire 21st century with such precision, such accuracy, that you could spot a single penny out of place. Sounds tricky? Well, it's not good enough. You've got to track it so well that you could find 0.00001 penny out of place, 10 to the -5 pence out of the entire budget for the century. That's what a measurement with precision 10 to the -21 means. Sounds incredible, you know, when I spell it out this way. Track the entire budget to the point where you can find a penny out of place in a century. And by the way, I've already made a 24% rounding in there. So I've actually skewed it already, but nonetheless, you're trying to find much less than a penny in a century. Sounds incredible, but this is what gravitational wave detectors have done. And in fact, when you read about the results from LIGO and the other gravitational wave detectors like Virgo and Kagra, what you're reading about is almost certainly the most precise measurements humanity has ever made to this point. I'm willing to, if you know, you can't prove these things in the absolute. So if anyone knows a more precise measurement, please tell me. But as far as I know, that 10 to the -21 measurement is the most precise thing we as a species have ever measured. So how do you see something so small? I'm going to tell you. When I was a PhD student, I had discussions with another PhD student who was interested in gravitational waves, and I told him we were never going to find them. I told him they probably exist. They're a natural fallout from Einstein's theory of relativity, but they're simply too small. We can't measure anything that small. You know, the size of a proton is 10 to the -15 meters. How do you get that small? Well, you use an interferometer, which is measuring differences. And that's where the power of these gravitational wave observatories come in. You've got these two long arms that you saw in the photograph. You see them here in this cartoon. How do they work? So you have a light source that fires a beam into the detector, and you've got a beam splitter. So it sends half the beam one way and half the beam another way. And then it reflects and comes back, and the combined beam is sent into a photodetector. Now, light is a wave. When you split it in half, you get these two different halves. And if they're aligned, if they're in phase with each other, when you add them together, you get constructive interference, and you get the same wave, but with twice the amplitude. And so you just get back what you started with. However, if you adjust the difference in these two legs slightly so that it's off by half a wavelength, instead what comes back is skewed by half a wavelength. So this minimum is where this maximum is, and vice versa. And so for every point on the top, you have the opposite point on the bottom. When you add them back together, you get nothing, because everything, every part, every of the wave from the top is added to its exact opposite from the bottom. Effectively, you build this big, expensive apparatus, you shoot a beam of light in, and if there's no signal, you get nothing out. Then you get somewhere a spiraling infall of neutron stars or black holes, causing space-time to undergo this strain, where you get this, in this wave pattern, you get this compressing and this stretching, as you see in the original LIGO observation. And that causes the destructive interference to not be perfect. It causes these two waveforms to not be exactly opposite each other. And so suddenly you start getting the signal out, and that's the signal you see here that tells you there was a gravitational wave there. That is how you measure something so incredibly small. As of right now, in 2022, there are 4 gravitational wave observatories in operation. The big announcements from LIGO in 2016 came from LIGO Hanford and LIGO Livingston at opposite sides of the US. Why did they do that? You can see here the Livingston and the Hanford data on top of each other. It's because if you have only one observatory and you see a signal, how do you know there wasn't just a little bit of seismic movement where you are? How do you know maybe, there wasn't some human-caused disturbance that just moved the mirrors relative to each other slightly? Space-time didn't do anything particularly exciting. It was just some ordinary movement that caused the mirrors to be slightly out of this half-phase difference. If you have 2 observatories that are over 1,000 miles apart, and they give you the same signal, as you see here, these line up really, really well, then you're confident that you didn't have some sort of minor earthquake in Washington state and at the same time get the same disturbance in Louisiana. And so that's how they were able to confidently release their results. Since then, Italy has launched the Virgo Observatory, and in Japan, you have the Kagra Observatory, which stands for the Kamioka Gravitational Wave Observatory. And so you have 4 running so far. We're not stopping there. India is building its own LIGO, which LIGO India will be running from 2025, so 3 more years. Since the first announcement in 2016, and really the first observation in 2015, many neutron star, and black hole mergers have been seen. This shows a list of all the observations since 2015, or actually, since that's the first one, all the observations since ever. And you might be thinking, well, that's great, but I actually can't read anything on this slide, so what are you trying to teach me? That's a good point, so let's make it bigger. This is what each of the observations on the slide tells you. The key tells you what was merged, so in this case, black hole, neutron star, what the primary mass of each of the bigger object was and the secondary mass of the smaller object was, what the final mass of the combined object was after the merger. The units are in solar masses, and the date and time that it occurred. So for instance, 2019, December 19th at 16:31:20. Of course, this is just the key. You can't see all of these wonderful events in detail. We don't have time to go through them tonight, So what I've done instead is I've given you the URL, and you can go to the LIGO site at Caltech yourself, and you can download this image and you can look at it to your heart's content. Let's talk a bit more before we move on, though, of gravitational waves in the context of multi-messenger astronomy. In 2016, I said the first gravitational wave signal was seen. 2 years later, gravitational waves were detected in coincidence with a gamma ray burst observed by the Fermi Gamma Ray Space Telescope. And now that is really multi-messenger astronomy, where you're seeing gamma rays and gravitational waves from the same object. And that was really cool. And in fact, that leads us into the next topic, gamma ray astronomy. This is a signal from a gamma ray telescope. I'll tell you how they work in just a moment. So how do we detect gamma rays on Earth? Gamma ray, the Earth's atmosphere is opaque to gamma rays. We cannot detect them directly. The smaller gamma ray telescopes are space-based. Like if we go back here, I said the Fermi Gamma Ray Space Telescope. Problem is, space-based telescopes are limited in how big they can be because you do have to be able to launch them into space. And so they're really good for seeing the lower energy gamma rays, of which there are many. They're not so good at seeing the really high energy gamma rays, which are more limited, and so you need bigger telescopes, bigger apertures to see them. I don't need to tell a group of an astronomical society how important bigger apertures can be. And so these need to be based on Earth. So, how do you get around the problem of the Earth being opaque to gamma rays? What you do is you don't look at the gamma ray directly. You look at the shower created in the atmosphere by the gamma ray. So the gamma ray strikes the atmosphere. Specifically, it hits, let's say, a nitrogen molecule, because 70% of the atmosphere is nitrogen, or almost 80% of the atmosphere is nitrogen. And in doing so, it collides with that nitrogen, and you get pair production. You get an E+, E- pair, an electron and a positron. Those go on and interact with other molecules in the air, both nitrogen and oxygen. And as they slow down, they emit something called bremsstrahlung radiation, or braking radiation, from stopping. Radiation is just photons. They emit energetic photons, which hit other molecules of air, which gives you more pair production, more bremsstrahlung, just rinse and repeat, basically. The point is, there's so much energy. Some of it at each point of the way is being converted into mass, E+, E- pairs. That's, we talked about earlier, E equals mc squared. What we do, we can't see the gamma ray directly on the ground. We can use ground-based telescopes to observe these showers. And by the way, just as an aside, what I just described about gamma rays is shown here. It's very similar to the method used to observe ultra-high energy cosmic rays. We talked about cosmic rays earlier. Your cosmic ray hits the atmosphere, so there's your nitrogen, and causes because it's actually made up of other matter rather than being a high energy photon. You actually get more particle, from a particle perspective, more interesting things coming out, like these pion particles. You also get photons, and these go on into the pions, can interact directly with nuclei rather than just with the electrons of the air molecules, and so forth. Because of the difference, gamma ray induced showers have a different particle content, and they also peak at a different height in the atmosphere than these hadron induced showers. Hadrons just being nuclei and their constituent components. Anyway, let's talk through, now that we've said how we can see them in terms of the showers they produce, let's talk about how we see those showers. We do it with something called an imaging atmospheric Cherenkov telescope. Here's how it works. Gamma ray comes in from space and creates this particle shower that we just talked about in the cartoon on the previous two slides. Those particles, those E+, E- in particular, are moving faster than the speed of light in air. That's how energetic they are. In air, light goes about 1% slower than it does in a vacuum. So these particles are breaking the speed of light in air. And when they do that, they emit a type of radiation called Cherenkov radiation. So the Cherenkov light can be seen by these imaging air Cherenkov telescopes on the ground. This happens about 10 kilometers up. The light can make it to the ground. And what's the signal you'd see from something like this? It looks like what we saw at the start of this section. It looks like a smear on the telescope where each of these little pixels is a photosensor, is a photomultiplier tube. So great, you're seeing the shower, but actually this is not so good, because how do you know where that streak that produced it came? If you can see my arm on the screen, I could line my arm up with that streak on the telescope, but I can also rotate it left or right, and it would still be lying on there. So you don't really know where the gamma ray came from. We can solve that problem by adding multiple telescopes. And when we do that, each of them has their own streak. And if you fit each of these streaks, then you can unambiguously pinpoint back to the source. If that sounds confusing, think of it this way. When you use binoculars to look at the moon, you can see with more precision than if you're using a telescope, because both eyes are in play. And in fact, even without any instruments, my eyes are what give me depth perception. And so you're just employing the same concept. You're seeing the same thing from several different instruments that are offset from each other in order to really nail down its details. So there are these gamma ray observatories all over the world. There are some on the Canary Islands, that's called MAGIC. I've got a good friend who works on the US-based Veritas. The original discoveries were made of gamma rays were made by Hess. That is based in Namibia. I remember it was the Cosmic Ray Conference in 2003, and Hess was the star of that conference because they had just used their imaging air Cherenkov telescopes to measure gamma rays. Australia has the aptly named Kangaroo, and so forth. So for instance, let's take a closer look. Hess came first, so we'll look at it first at the Hess telescopes in Namibia. So there's your 4 telescopes. This is what a cartoon of what one of them looks like. Here is what the camera looks like. So there's the pixels that give you, I'm going to go back, the images we saw. Well, maybe I'm going back too far. That's all right. The images you see on this slide, you see how the image I showed you has this shape to it. Now you can see why. It's because the camera, that's the shape of the camera. You can see the jagged edges there. The camera has 2048 pixels. Each telescope has a total aperture of 10 to the 8th square meters. So they're 12 meters diameter each. And then they added a larger telescope, 28 meter diameter, to the 12 meters ones since July of 2012. Bigger aperture means you can see dimmer objects. In other words, lower energy threshold of 30 GeV. As I say, it's not the only game in town. You've got Veritas in the USA shown on the top. You've got the MAGIC telescope on the Canary Islands shown at the bottom. Again, these larger telescopes are giving you lower thresholds, and you can see that actually the mount is designed to have fast slewing so that they can actually respond. These are gamma ray telescopes. If a GRB goes off, they can slew quickly to try to respond to a GRB alert and see the GRB signature. The 2 telescopes are able, in Veritas, are able to operate independently. And the camera has this interesting design that you can see here, where you've got 1-inch photomultiplier tubes, 1-inch photosensors in the middle, and 1.5-inch ones on the outside. And so that means this middle region is more densely instrumented. You have smaller phototubes, which means you've got smaller pixel size and therefore greater resolution. The outer region has worse resolution. You might ask, why do you do that instead of just using good resolution, the best resolution throughout? It's a very simple answer. More tubes is more money. So you get your good resolution in the center and then your poorer resolution on the outside. So here are some images of gamma ray sources that were seen with Veritas. one way that you can one thing you can do with your gamma ray observations is actually build up a catalog of sources you see. So when you observe a gamma ray source, you note where in the sky it is. These are galactic coordinates, and you can try to identify them. So these orange blobs are active galactic nuclei. The green ones are gamma ray sources in the egret catalog that have not yet been identified. That's the majority, although if you look, you can see, for instance, there's a solar flare, and the Large Magellanic Cloud is over here. And there are some pulsars, those are the squares, but most of it is either AGN, active galactic nuclei, or unknown. One source of gamma rays is the Pulsar Wind Nebula, the Crab. You're probably very familiar with that. And so this is the observation of a medium energy gamma ray flare that was observed by the Agile telescope. Here is what you see inside the Crab. This is the centroid position of that excess of TeV gamma rays. And you can see it's very close to the pulsar position, certainly within the systematic uncertainty, which is that big. And so that's really quite interesting. Going forward, just as I've told you how the the gravitational wave observatories are moving on to build more facilities, the future of TeV gamma ray astronomy is the CTA, the Cherenkov Telescope Array. Does what it says on the tin, right? And this involves two different sites, northern and southern hemisphere. I certainly don't need to tell you guys why you'd want to look at both the northern and the southern sky. I think everyone here knows that they're different. And there are three different telescope designs. Just like I talked to you earlier about having larger and smaller telescopes, you actually have large telescopes, medium-sized telescopes, and small telescopes looking at different energies and having different capabilities. So actually, before I move on, I should say, at the end of the gravitational wave observatory section, I talked about how gravitational waves did multi-messenger astronomy. It's already, I hope, clear how gamma rays have done so, because the 2018 event was both gravitational waves and gamma rays observed from the same event at the same time. So let's move on to neutrino astronomy. Neutrinos work through neutrino detection works largely through water Cherenkov detectors. You have some sort of transparent medium, could be water, could be ice. You instrument it with light sensors, because as a neutrino comes at or near your detector and has an interaction, what we call a charged current interaction, it changes the neutrino into a charged lepton. That's the charge of the charged current interaction. Either an electron, which is a lepton, or one of its heavier cousins, like the muon or the tauon. And that streaks through your detector, moving faster than the speed of light in water or ice. So once again, you get Cherenkov light. And you have these light sensors, these PMTs, in order to detect them. Okay, great. How do you find them? Because there's a lot of backgrounds, and neutrinos very rarely interact. So one of the backgrounds is cosmic ray muons. You can avoid those by going deep, so under a mountain or under the ocean. That's one way to help reduce your cosmic ray muons. You can also look down instead of looking up. Neutrinos pass through almost anything. So if you're looking up, you may see neutrinos that are coming down, but you can also see cosmic ray muons coming down. If you look down, neutrinos going through the Earth, no problem. Cosmic rays going through the whole Earth, that's not going to happen. So you have actually, you have your telescope in the northern hemisphere looking at the southern sky, and vice versa. And in fact, before I finish this slide, I just want to show you probably my favorite logo ever for an experiment. This is the old Amanda experiment, which was a neutrino telescope at the South Pole. It stood for Antarctic Muon and Neutrino Detector Array. And you can see you've got at the South Pole in Antarctica, a penguin with a telescope, pointing the telescope down at the ice to look at the neutrinos that came from a star and are going through the Earth. And actually, it's super accurate, because that's basically what happens. You're looking, you're at the as far southern hemisphere as you can go, and you're looking at the northern sky. Also, atmospheric neutrinos are a background. Atmospheric neutrinos are a great signal and have produced literally Nobel Prize winning physics. But if we're looking for high energy cosmic neutrinos, they're our background. We can't get rid of them. But if you look, these are the spectra of neutrinos at all energies. Like these are solar neutrinos in blue and supernova neutrinos in red. Here's atmospheric neutrinos, and you can see they fall off very quickly with energy, whereas sources of cosmic neutrinos go out to higher energies and drop off more slowly. So you can use the energy to try to pick them out from atmospheric neutrinos. And you'll actually see an example of that in just a minute when I talk a bit more about how these cosmic neutrinos were first discovered. So there's the logo again. How can you tell what you're looking at? How do you do particle identification? So this is the Super Kamiokande detector, which Steve mentioned I have been scuba diving in. Beautiful, really beautiful detector. It's under a mountain in the Japanese Alps. Those are two poor Japanese postgraduates who had to clean all of the phototubes. These are what the phototubes look like. Each of them is 20 inches across, so about that big. And when you have a muon, again, heavier cousin of the electron, it's what we call minimally ionizing. It doesn't have much ionization, and therefore it gives you this very sharp ring of light in your detector. Whereas the electron does cause atoms to ionize, and so you see this very, very fuzzy ring in there. And as I say, I've been scuba diving in there, so if you have a particle physicist in the detector, you get an extra bit of fuzziness. In larger detectors like IceCube, you actually get from muons a track that's like 1 kilometer long. So you get a very long track throughout your detector. That tells you it's a muon, neutrino. Whereas you get shorter tracks from electron neutrinos because they lose energy more quickly. If you get the new tau, which produces the heaviest lepton, the tau lepton, you actually get this weird signature, what we call a double bang. You get the first signature from the charge current interaction that produces a tau, just like you do here from this long track of producing a mu and the short track producing an e. But then the tau decays. It's a very heavy particle. Heavy particles decay to lighter particles. And so you get this decay, and this decay gives you a second signature in your detector. So just as I showed you where the world's gravitational wave observatories are and the gamma ray telescopes are, let me show you where the neutrino telescopes are. So you have at the South Pole, we've talked about Amanda and IceCube. Then you've got the Russian telescope in Lake Baikal, and you've got Antares and soon to be KM3 in the Mediterranean. So let's start with the Russian one, Lake Baikal. The original telescope in Lake Baikal was a central core, you can see here, heavily instrumented with 96 pairs of optical modules on 8 strings. So that's what you see in the middle here. 1, 2, 3, 4, 5, 6, 7, 8 strings down, heavily instrumented. So around that, you have a perimeter, an outer ring with 3 additional strings, each equipped with 6 optical module pairs. Just like you saw with the gamma ray telescopes, you've got a very well instrumented central region for best resolution, and then an outer region that's less well instrumented. Again, why not make everything as instrumented as possible? It just comes down to money. Each of these optical modules is equipped with a PMT like the ones you saw in Super K. Those were 20 inches or 50 centimeters. These are a little smaller. They're 37 centimeters. And how do they get them to the bottom of Lake Baikal? Lake Baikal is the world's largest freshwater lake, and being in Russia, it freezes over in the winter. So you just drive out on top of it and use a winch to lower it into the lake. You drill a hole in the ice and down it goes. Antares, on the other hand, goes 2.5 kilometers deep in the Mediterranean. Antares uses 885 optical modules. Here's a picture of one. So you got a phototube, like I showed you before, in this enclosure. And these are arranged in triplets. So you can see each point on the line with PMTs has 3 of them and they're offset by 120 degrees. So you can see in a 360 degree field of view. Looking downwards, we talked about that earlier. You look downward for your light to reduce the backgrounds of stuff coming down at you from above. Each of those contains a 10-inch PMT. The Mediterranean is not a quiet environment. Things move around. And so each of these is equipped with acoustic transponders so that you can tell where your sensors are at any given moment. I mean, they're not going to move a mile away, but if you want to do precision measurements, you want to do precision observations, you need to know exactly where it is. If it's moved this far, that's going to mess things up. So let's take a closer look. I showed you the cartoon, but this is actually what one of these looks like being put together. So there's one of these points where you've got 3 optical modules that goes down. There's a whole bunch of them put together. You can see all of these getting loaded onto a boat. You've probably noticed, unlike Lake Baikal, the Mediterranean doesn't freeze over. And so instead of driving out onto the ice, there is no ice. So you put these things on a boat and then you deploy them into the Mediterranean. I got to tell you, Antares was deployed around 2004, 2005. The successor, which I'll talk about in a moment, KM3net, is in the process of deployment now. And I'm going to Marseille at the start of September, and I'm giving them a seminar. And then on September 5th, and I was told by the spokesperson of KM3net, the successor experiment to Antares, that actually I'll be there on a Monday. They said 2 days later on the Wednesday, they'll be taking a boat out to do a deployment just like this, loading the optical modules on a string onto the boat and deploying, and asked if I'd like to join. So I got to tell you, I am just excited as anything that I guess Wednesday, the 7th of September, I'll be going out to see this deployment in person. So really cool. Okay, let's get on to IceCube. IceCube works very similarly to the previous two, except Baikal and KM3net and Antares all deploy in water. IceCube does what it says on the tin. It's a cubic kilometer of ice. And so this is what's deployed down here. You've got your strings that go 2.5 kilometers down. The first 1.5 kilometers is not instrumented. The instrumentation's all down here. The reason it goes deep is because this is where you have some really clean ice, so the light transmits really well. And then you've got these digital optical modules, just as you saw for Antares. How do you get them down there? I told you on Lake Baikal, you drive onto the top of the ice when it's frozen, you cut a hole in the ice and put them down. Antares and KM3net, you take a boat out. Well, this is ice, but it's ice all the way down. You can't cut through it. So what do? IceCube uses high pressure hot water to drill a hole 2.5 kilometers down at the South Pole, then lowers the string with instrumentation down, and over the next few days it just refreezes, and there you go. Bob's your uncle. You've got your detector in place. So 86 strings make up IceCube of digital optical modules. They're set 125 meters apart, except in the center deep core where there's where it's more densely instrumented. I think you understand why at this point. You have a smaller region of high instrumentation, same as we've seen several times now. And vertically, the optical modules are spaced 17 meters apart. Also, we talked a little bit about cosmic rays as another messenger. And on top of IceCube, you have IceTop, which is a cosmic ray observatory sitting directly on top of the neutrino observatory. So this is the largest existing detector. It instruments a cubic kilometer of Antarctic ice. The precursor, Amanda 2, I showed you its logo, was very similar to Antares in size and sensitivity. And here's a better picture, a close-up of them lowering a string after having drilled this high-pressure hot water drill of going down 2.5 kilometers in the ice. This is also a close-up of what one optical module looks like. You've got a photomultiplier tube, as we were talking about. You've got this mesh to shield from the Earth's magnetic field. And then you've got all your electronics. Everything you need has to be in there because it's 2.5 kilometers under the ice. So you've got your, a Cockcroft-Walton device, which generates high voltage. You've got LED for calibration. And then you've got your electronics readout board there. Also, you've got this sphere to protect it from pressure, because otherwise the PMT would just get crushed under all of that pressure. We've talked about what IceCube is. Let's talk a bit about the results from it. So the first statistical evidence, actually, no, before I get to the statistical evidence, let's talk about some individual events. So the first high energy neutrino event seen in IceCube, you got this pair of events in 2012. Let me tell you what they mean. Each circle represents one of those digital optical modules that, you see one going down here. Here's the cartoon of what it is. Each of those represents one that got hit with light. The color tells you when it got hit, and the size of the circle, all the optical modules are actually the same size, but the size here tells you how much light hit it. And in 2012, you got these two big events that they named after Sesame Street Muppets, as you do, and they named them Ernie and Bert, which were very impressive until 2 years later, they got this massive event, which they went on to name Big Bird. I've actually seen t-shirts made with Big Bird on it. I mean, the IceCube event, not the Muppet. Well, that's great, but to do physics, we need to actually do more than just see events. We need to understand the astronomical events we're seeing. And the first statistical evidence for high-energy astrophysical neutrinos was released by IceCube in 2016. This is what they showed at the Neutrino 2016 conference. The data is in these black points. So this is energy on the horizontal axis, and this is how many events they saw in 1,347 days. That's great. That's the data. You might be asking, what's all this stuff? Do you remember I said earlier you had some backgrounds that were irreducible, like atmospheric neutrinos? So what you do is you use the different shape of the spectrum. Atmospheric neutrinos drop off more, have a lower maximum energy and drop off more quickly, so you can statistically tell them apart. Well, for instance, blue is the atmospheric neutrinos. I don't know if you can read that. It says background atmospheric neutrinos. And all the other backgrounds are shown here as well. The total background from atmospheric neutrinos is shown in this orange line, in this purplish orange line, and you can see the data exceeds the expected background. Not at lower energies, it's quite consistent with the background for these first three bins, but as you go out, it exceeds it. And so that tells you statistically, 54 events were expected, but only 20 plus or minus 6 of background events were expected. So you get 7 standard deviations, 7 sigma significance of energy evidence for extraterrestrial neutrinos. Antares in the Mediterranean also made a similar observation, but because it's smaller, it wasn't so statistically significant. 13.5 plus or minus 2 means that actually you're not really too far off from the observation is higher, but not too far off from what's expected. And that's not surprising because Antares is smaller. So IceCube in 2016 made waves by showing us a statistical evidence for astrophysical high-energy neutrinos. That's not good enough to do astronomy, though, is it? You can't just say we saw something. You have to say, where did it come from? And that's where we come back to the multi-messenger approach. In 2018, 2 years later, there was a breakthrough when their first source was seen. An observation at IceCube of high-energy neutrinos were seen from a blazar and confirmed by all these other optical detectors. This was a great leap forward for multi-messenger astronomy. You got the gamma rays we were talking about a few minutes ago and the neutrinos at the same time. And in fact, this made the cover of Science magazine back in 2018, just 4 years ago, that neutrinos from a blazar had been seen. That's neutrino astronomy. Statistically significant excess is a good first step. But you have to be able to say, actually, we saw cosmic neutrinos and we know where they came from. And that's this cartoon you see here. This is an artist's conception of a blazar. Remember, a blazar, we can see it because the jet is pointed towards us. And if you look closely, you can see coming directly at us, you've got all these gammas representing light, gamma, 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 gamma. And coming in nearby is you've got to the South Pole, you've got the neutrinos, new coming down. So that's the artist rendition. Just as I talked about the next generation of gamma ray telescopes and gravitational wave observatories, think technology marches on with next generation water Cherenkov detectors. In fact, what I'm showing you here is part of a New York Times article from just last year, hunting ghost particles between the world's deepest lake. The upgraded Baikal, now called Baikal GVD, Giant Volume Detector, is now operational. It's about as big as Ice Cube. So this is the first of the next generation water Cherenkovs. The future is not somewhere out there. The future has already begun. Similarly, KM3net is under construction. I told you next month, I'm so excited to be going out and being part of one of the deployments. So this will be also like the upgraded Baikal will be about Ice Cube sized and will be located at several spots in the Mediterranean. Ice Cube, you may hear me saying, Baikal, KM3net are catching up in size. Ice Cube's not resting on its laurels. The red is the existing Ice Cube and Ice Top. Ice Cube is planning Ice Cube Gen 2, which both stands for Generation 2 and is simultaneously a penguin pun. That takes talent. Ice Cube Gen 2 involves two things. One is a much larger instrumented region that is more sparsely instrumented, coming back to the same theme you've heard 3 times already. There's your inner high. The existing one is more highly instrumented. The new Gen 2 would be a much bigger aperture with lower resolution, plus an even more instrumented area inside called, so there's deep core in green, and you can see this grayish region here that's called Pingu. That's even more highly instrumented. Deep core exists right now. Pingu would be new. So we're coming to the end of the hour. Other topics, I didn't get to cover everything because as I said at the beginning, it's a bit of a whistle-stop tour through multiple topics. One of the topics I didn't talk very much about was cosmic rays. I mentioned Ice Cube, for instance, has Ice Top to see them, and there's also searching for cosmic neutrinos with cosmic ray detectors like Pierre Auger. But every one of these topics, cosmic rays, neutrino astronomy, gamma ray astronomy, gravitational waves, each of these can be an hour-long talk on its own. So we can't get to everything. One of the things we can't get to in detail, but I still want to mention in passing, because it's near and dear to my heart, is supernovae. As you heard at the beginning, Steve said I did my PhD looking for supernovae in the early universe through their neutrino signature. This is a picture of supernova 1987A, or its remnant. And just as recently as April, just this spring, just a few months ago, I attended a workshop on supernova neutrinos in the multi-messenger era. So, supernovae is another area where multi-messenger astronomy is really starting to play a role. You can see I gave the talk on water Cherenkov detection of supernova neutrinos. Electromagnetic follow-up with photons like gamma rays was covered here in this talk, and also the talk of the new robotic telescope. A very gamma ray particular talk was given by Paula Chadwick at the University of Durham, talking about very high energy gamma rays from supernovae, and talking about the CTA, the Cherenkov telescope array that I talked to you about earlier. Meanwhile, there was a talk also linking gravitational waves to supernovae. So all the bits I talked about today, you can see them here. Water Cherenkov neutrino detectors, gamma ray telescopes, gravitational waves. I will also say the last talk of the day was a talk by John Ellis that I did not understand in the slightest, but I'm very glad I got to hear it. Anyway, we're just about out of time, and I want to make sure you have time to ask me questions. So I'm going to sum up by saying astronomy's messengers up to the 20th century was just visible light photons. In the mid-20th century, we moved on to multi-wavelength astronomy. We were still using the same messenger, light, photons, but we got many different wavelengths in. By the end of the 20th century, we had neutrino astronomy. In fact, the 2002 Nobel Prize was awarded in part for the invention of neutrino astronomy. And in the early 21st century, we added ultra-high energy cosmic rays, and whoops, sorry, the text got deleted. It should also say under here, it should say gravitational waves. I'll have to fix that. So when you ask, what do you learn with multi-messenger astronomy? The best analogy is to look at each messenger like each of the 5 senses. You don't want to say, well, if we can see light, who cares about the neutrinos? Or if we can see neutrinos, who cares about the gravitational waves or the cosmic rays? Just because I can hear you doesn't mean I don't learn more by being able to see you and hear you at the same time. Or just because I can smell my food doesn't mean I also don't want to taste it. Multi-messenger astronomy is combining complementary information from each mode, just like our senses do, to give us the best possible information about our universe. And as I said at the beginning, this isn't an end, it's a beginning. The multi-messenger era has really just begun in the past decade, really I would say since 2016 or 2018. So there are many more exciting times ahead. And I'll stop there and ask if you have any questions for me.
Matthew, thank you very much for a fascinating talk. Could I ask you to stop sharing your screen?
You can indeed.
And then we'll move on to questions. I have one about detectors like Antares. How do you cope with the fault signal from bioluminescence?
That is an excellent question. So you do have different backgrounds in the different environments. For instance, you don't have bioluminescence in Ice Cube, but exactly, you have it in the Mediterranean. And so one of the things you have to look at is the type of signal you get. So I'll joke sometimes when I teach a postgraduate course on particle astrophysics. And so we go into each of these topics in more detail. And I'll joke that your background is fish. But actually, most of your bioluminescence is not fish, it's algae. And so you get specific wavelengths, and you also get specific patterns. And so you have to train your data to cut those out, because you're exactly right that bioluminescence is a background. It's a background we can identify and cut, but we have to do so. It's there in Antares.
Okay, thank you for that. So I'm looking for questions. We're going to start with Mick Nichols. Mick, can you unmute yourself, please?
Hi. On one of your slides, you showed like a map where things had been detected. And on one of them, you said a solar flare. Now, I'm a bit curious about that, because I'd have thought in your line of work, a solar flare is the last thing you want to be detecting. So how did that end up on there?
It was that's absolutely right. It's not terribly interesting for looking into deep space, but if it gives a gamma ray signature, it will be picked up by the gamma ray telescopes and has to make it into the catalog. I'll tell you, by the way, I'm so glad you asked about the catalog, because one of the things you've given me the opportunity to do is talk about briefly about another multi-messenger topic that I didn't have time to talk about here. I talked about overlaps between some of the various messengers. Another one is to look for neutrinos from a gamma ray burst. And how do you do that? Because you don't even know that they give off neutrinos. And if they do, you don't know, do they happen at the same time as the light? Are they earlier? Are they later? And so what we do is we take a neutrino telescope like Super Kamiokande, and you take a gamma ray catalog like the one we were just talking about, the egret catalog, and you just look at 1 second around the gamma ray burst, 10 seconds, 100 seconds, a day, and just try to compare that with the background when you're far away from any gamma ray burst. And you're just basically on a fishing expedition to see if you can see an excess of neutrinos in proximity in time to a gamma ray burst, without actually knowing how close it should be. So far, we've found nothing, which is why it's one of the topics I omitted, It's an active area of search, but there's no discovery yet. But that's another type of multi-messenger astronomy, this time gamma rays and neutrinos, looking for GRBs.
Thank you.
Happy to help.
Matthew, while you've brought up this fishing expedition that you go on looking for neutrino bursts, is there any time lag between the different messengers?
So it depends on the messenger. For instance, we talked at the end about supernovae. In a core collapse supernova, the neutrinos are emitted directly from the exploding star. As your star explodes, it leaves behind an extremely hot proto-neutron star, and that rapidly cools off through neutrino cooling, through emitting neutrinos. The light is emitted a few hours later due to the decay of radioactive elements that are created by the shock wave moving out through the supernova. And so you've got a 3-hour time lag with neutrinos first, light comes later. And we saw that when we saw neutrinos from 1987A. That was actually a sort of a proto multi-messenger discovery. Now that's true for supernovae, but for a gamma ray burst, we don't really know what the relation is. Will the neutrinos come first? Will they be at the same time? Will they come later? And that's why we do that fishing expedition. And I do have to admit that this is 2 or 3 questions in a row I've now answered with some reference to fish, which is entirely unintentional. And so I'll try to keep seafood out of it for my next answer.
Okay. Andy Davey.
Hi, Matthew. Excellent talk. I've really enjoyed it. So thank you very much for that. Couple of parts of my question. First one, I actually live outside at Mediterranean down in southern Spain. So the question is the Antares one is, are the detectors actually anchored to the seabed to keep them stable?
They're not anchored, but they are dropped down with weights. So
right.
they do move around, and that's why they're not going to drift off, but they'll definitely go back and forth. And the acoustic transponders keep a fix. They can't stop them from moving, but they do mean when we see light, we also know where the detectors were when they saw the light.
Okay, this next one's a bit more difficult. So if we do detect dark matter particles, do you envisage in maybe 100 or 200 years time dark matter detectors for another medium for astronomy?
So I hope it's sooner than 100 or 200 years. In 2016, there's every 2 years that one of the major dark matter conferences called IDM, which stands for Identification of Dark Matter. And in 2016, we hosted that in Sheffield. And during the closing talk, the final speaker said, dark matter was first proposed or first observed, its existence was first noted in 1933 by Fritz Zwicky. He challenged us, the younger scientists in the audience, to find it by 2033, by the 100-year anniversary. That was 6 years ago. 2033 is 11 years in the future. Let's see if we can do it. If we are able to really nail down what the dark matter is, it is potentially a future messenger to add to the list, as you say. And interestingly enough, even without knowing what they are, we're already moving in that direction, because I showed you the ice cube detector. And I showed you how it goes down 2.5 kilometers into the Antarctic ice. On a few of those strings at the very bottom are dark matter detectors. It's an experiment called DM ice, for dark matter ice. And those are dark matter detectors sitting at the bottom of ice cube strings. So we're already moving the technology in that direction.
Okay, thank you.
Happy, always happy to answer an interesting question.
Okay, I'm looking around looking for any other questions. Tony Morris.
Hi, Matthew. Can you hear me?
I can hear you very well. Hi, Tony.
Hi, Matthew. On the slide where you were showing the 2 objects colliding and emitting gravitational waves, there was a significant difference when they got the total mass at the end.
Like this?
Keep going. It was the single.
That one.
No, next one again. Keep going. And again.
Maybe it was this?
That's the one. So the final mass was 32 solar masses, I presume.
Yes.
So how much of that is gravitationally taken away, and how much of it is other particles?
Most of that is, so the missing, so what you're saying, just to make sure we're on the same page and to make sure everyone else is too, 31 plus 1.2 should equal 32.2. The fact that it doesn't means that there is 0.2 solar masses, which is not trivial, right? The sun's got a lot of mass. So a fifth of the sun's mass carried away. And you're basically asking, where did it go? Was it all in gravitational energy? And the answer is basically yes.
Okay.
Okay, Tony?
Yeah, fine.
Yes. So I'm looking around, I'm looking for any other questions, in the room? Roy Ganson?
I was just really going back to the ICE project, these things 2.5 kilometres under that. I'm presuming they're not planning to get them out. They're there permanently.
That's correct. The strings in the Mediterranean are conceivably recoverable. The strings in the ice. Let's just say if we survive as a species, 1,000 years from now, archaeologists will be digging them out to understand 21st century technology.
Unless they've melted out with global warming since.
Okay, that is one way to get them out. Yes, exactly. Melt the South Pole ice and out it goes.
Okay, Roy. Peter Lloyd.
They won't come out in a glacier then. No. Sorry, my question doesn't relate directly to your talk, I'm afraid, which I enjoyed immensely, but it left me sort of, but in it, you showed several slides showing these huge telescopes that you use as the various detectors. There were the ones at Hess, for example. None of them had any means of protection. Do they not need protection from rain and snow and dust and wind? And
yeah, those are kept outside. Now they are generally in dry environments, so you're not going to get snowed on in the desert of Southwest USA or in Namibia. But it's true that you have to then clean them off every now and again from dust and whatnot. They're not. It's absolutely true. They're not enclosed.
Yeah, I was just intrigued that they don't appear to need to be enclosed.
That is, in fact, that's a really good observation. I think nobody has ever, I've given various talks involving them before. Some are just gamma ray astronomy, one topic talks, and nobody's ever noted that before. So well spotted.
It so happened I saw a picture not long ago of a telescope in the Canaries up at, I've forgotten the name of the mountain, and that wasn't covered either. And I thought, well, doesn't it rain there? And the answer seemed to be it's too high to rain up there, but they get a lot of fog.
Yeah, fair enough. Fair enough.
Okay, well, thank you.
Thank you for that question. I really like that.
Thank you, Peter. And I'm looking around once more for any more questions. I don't see anybody, and I think we've worked Matthew hard enough for this evening. So thank you very much for breaking into your holiday, or letting us break into your holiday, Matthew. I hope you're going to pack your scuba kit for the 7th of September. And,
follow the tubes down. That would be the
a-
second water Cherenkov detector I've scuba dived in. I don't know if anyone has ever scuba dived in 2 before.
No. But you could actually say that you swam above it. It's so there you are. Matthew, thank you very much for an excellent talk. Can we please give Matthew Malek a big Mexperience in Astronomical Society? Thank you. Thank you, Matthew.
Thanks.
Thank you all. Have a good evening. I hope to see you again soon.